Okay, so welcome back. So last time we discussed Runge's theorem for compact sets. Maybe that was one class even before that, and then we proved Runge's theorem in general for any open set. The main point was to prove Runge's theorem for compact sets, and for a general open set, the idea was to use compact exhaustion, right? You remember compact exhaustion, right? Any open set can be written as an increasing union of compact sets satisfying some of conditions. Uh, Kn is contained in the interior of Kn plus 1, and we also had importantly that S2 minus any compact set is contained in one of the Kns, and S2 minus Kn, any component of that contains a component of S2 minus omega. So this was compact exhaustion, and using this we proved Runge's theorem for any open set. I think that's all that we have done last time, and let me start sharing the screen. Can one of you confirm the screen is visible?
Yes, sir.
Yeah, it's okay. Okay, so let's start. Okay, so lecture 13. Yeah, so today the main points are one is what is called the Mittag-Leffler theorem. This also I mentioned in lecture 1, just the name. So Runge's theorem said that a holomorphic function can be approximated by rational functions with prescribed poles. We can pre-assign the poles of the rational function. Mittag-Leffler theorem will say that you can construct meromorphic functions where the poles are a set that is prescribed, a set that you have given me. The poles will be there. You can also prescribe what the principal paths at each of that pole should be. So you give me a set. Of course, you should not give me a set with a limit point because poles finally cannot have a limit point. So give me a set without a limit point. Then I can construct a meromorphic function whose poles are exactly the points where you have given me. You can also tell me what order the pole should have at a given point. I will make sure that this meromorphic function has that order at that pole that you have given me. You can also tell me that, look, this rational function should be the negative part of the Laurent series in the Laurent expansion, what is called the principal part. I can make sure that at that pole, the order is the same and the principal part is what the function that you have given me. All this can be managed together. This is called the Mittag-Leffler theorem. And after that, we will have a nice characterization of simple connectedness for a region. You take an open connected set in C, such a thing is called a region, and a region is simply connected. We will give a number of conditions. In fact, we will give nine equivalent characterizations of simple connectedness. Most of them we have already done, so it will be like putting them together. So that's what we will do today. Okay, so let's start. Let's start. 18 students are there. Okay, good. So last time we proved Runge's theorem in general, meaning for any open set. This followed immediately from Runge's theorem on compact sets by what we call compact exhaustion. And we followed the proof in Rudin for Runge's theorem, which was slightly conceptually advanced because it uses functional analysis, etc. So you should not think that Runge's theorem actually needs those things. That is just Rudin's approach. It's a good approach. It's a beautiful approach. So we followed that. But Runge's theorem is from 1885 or something, or even before that, 1885, I think. And the original proof was an elementary proof. It only involved complex analysis and nothing more. What is called shifting of poles technique, whatever. And when we looked at Sandy Grabiner's article, it was written that method is tedious, but I believe that method also can be presented in a nice fashion, and that is done in the book mentioned by the Wikipedia article. So anyway, we followed Rudin, and we also mentioned that there's a more elementary proof in Conway. Using that, the set M bar that we considered is not just a Banach space, but a Banach algebra. I mean, he doesn't have to use these words, but that was the underlying motivating observation. And so we may or may not come back to this. I hope we can come back to this, provided we have enough time. So this I'm not sure. This was originally due to Sandy Grabiner. And then, for Runge's theorem, the Wikipedia page actually mentions Donald Saracen's book. And I had a quick look. I did not read the full proof. That's even much more elementary. And maybe, this is original proof, which is presented in a easy to understand fashion. So this uses just Cauchy integral formula and some, basic techniques about either power series expansion or Laurent series expansion. Nothing more. That's a feeling that I got. It's quite elementary. So there are elementary proofs. You don't need all that Hahn-Banach and Rees representation theorem and all that, but that was a nice approach. Sometimes it's good to see how advanced tools can be used to give a very presentable proof. Okay. So we may come back, we may not. I don't know. Today we will discuss the Mittag-Leffler theorem, and this is about the existence of meromorphic functions where the poles are prescribed. The function will have poles exactly at the set that you have given me. Not just that, at each pole, what the principal part should be, what the rational function, the principal part should be, that also you can prescribe. So with prescribed poles, with prescribed principal parts. This is Mittag-Leffler theorem. We will, so I think this can be done directly, but we will do it as an application of Runge's theorem. We will also cover the characterizations of simple connectedness of a region in C. So we will present 9 distinct facts. All of them are equivalent, and each of them means simple connected. So that's what we will do, and in the discussion session, we will discuss whatever questions you may have. Okay, so let's do Mittag-Leffler. So omega is an open set in C, and you give me a set. So this is a prescribed set of poles. So you give me a set, make sure that it has no limit point in omega, because finally this is going to be a set of poles of a meromorphic function that we are going to construct. So it should not have limit points. So you give me a set without limit points. This is a prescribed set of poles, and this is going to be the set of poles of the function that we are going to construct. And we may prescribe the principal parts as well. So at each alpha in A, you also give me a function which looks like the principal part of a function that we are going to construct. So for each alpha in A, consider P alpha of Z to be, in like a finite negative part of a Laurent series expansion, so that this looks like the principal part. So you give me these things. So these are just rational functions, right? So you give me a set without a limit point, and for each point you give me m is m alpha. You give me a number associated to m, a natural number associated to m, and associated to that natural number you give me some finitely many complex numbers, c1 alpha, c2 alpha, cm alpha, and this function corresponding this function p alpha z. Okay, so now what we are going to achieve is to construct a meromorphic function whose poles are precisely the set A, the points of the set A. Not only that, if alpha is in that A, f is going to have a pole at alpha of order m alpha. Not only that, when you expand f around alpha, you write its Laurent series expansion around alpha, this P alpha is precisely the negative part of the Laurent series expansion. Is the statement clear? You have given me a set without a limit point, and you also have given me these functions associated to each alpha. Now we have to construct a meromorphic function on omega whose poles are precisely points of this set. Not only that, at each alpha, around alpha, when you expand that function f in its Laurent series expansion, its negative term, the principal part of the Lorentz series is precisely P alpha. This is what we have to do. So remember, we have compact exhaustion. This is our starting point. Choose Kn contained in omega for each natural number compact set such that we have these three conditions. Kn is contained in the interior of Kn plus 1 for each n. Every compact subset of omega lies in some Kn, and every component of S2 minus Kn contains a component of S2 minus omega, and this happens for each n. This is compact exhaustion. We have this, and now what we are going to do is the set that you have given me A, I'm going to intersect. So my A1 is A intersection K1. A2 is A intersection K2, not quite. I don't want to intersect with K2, but I will intersect with K2 minus K1. A3 will be A intersection K3 minus K2, etc. So consider these sets. So these are subsets of A. A you have given me, and I'm going to take A1 as A intersection K1, A2 as A intersection K2 minus K1, A3 as A intersection K3 minus K2, etc. Observe that each of this AN is a finite set. My claim is that each of this AN is a finite set. Why is that? Can someone tell me? These are all finite sets. Why is that? Yeah, I think Ariman is trying to say something, but okay, maybe it's my side. Can you repeat? I couldn't hear you. So I understood, but the voice is breaking also. So yeah, maybe every day the connection. So yeah, so the reason is A does not have a limit point. It does not have a limit point in omega. So A does not have a limit point in omega. So if so, An is contained in Kn minus 1. In particular, it's contained in Kn. And if it was not finite, it would be an infinite set inside a compact set, which will have a limit point in Kn and therefore in omega. Because it does not have a limit point, these are all finite sets. So that's what Ariman said, that's correct. So each of this is a finite set. And now I'm going to, so I'm happy to take a sum on these finite sets. So define Qnz to be summation alpha in An. So Qn is summing over An P alpha z. These functions you have given me. Okay, so this is a finite sum. So this is a finite, this is a rational function, right? These are all P alpha z is a rational function whose only pole is at alpha. There are finitely many such alpha in An. Sum all those. So Qnz will be a rational function with finitely many poles. So take these Qn's for each n. Each Qn is a rational function since An is finite, and the poles are exactly in the points of An. The poles of Qn are precisely the points of An. The poles of Qn are in An. An is A intersection Kn minus 1 by definition. And this is for n bigger than or equal to 2 because I'm subtracting. A1 was just A intersection K1. There was nothing to subtract. Okay, so each Qn is holomorphic in an open set containing Kn minus 1. Why? Because Qn has poles in Kn minus Kn minus 1. So they are all holomorphic in Kn minus 1 and in a small open set containing Kn minus 1. Because the poles are in Kn. And Kn minus 1 is contained in the Kn minus 1 is contained in the interior of Kn. Right? In compact exhaustion, each one is contained in the interior of the next one. So you can take an open set inside Kn containing Kn minus 1 and the poles are outside that. So each Qn is holomorphic in an open set containing Kn minus 1, and this is like Runge's theorem for compact set. So if you have a function holomorphic on an open set containing a compact set, you can approximate it by rational functions whose poles are prescribed from S2 minus the compact set. So in particular here, by Runge's theorem, there exists rational functions Rn with all the poles in S2 minus omega. So the poles can be prescribed. You can give me a collection which meets each component of S2 minus Kn minus 1. But each component of S2 minus Kn minus 1 contains a component of S2 minus omega. So I'm going to take my prescribed set from S2 minus omega. So I can make sure that Rns have poles in S2 minus omega. That's all that I need. Precise point is not required. So this is Runge's theorem, right? I can prescribe a set which meets each component of S2 minus Kn minus 1. But take that point from S2 minus omega. After all, S2 minus each component of S2 minus Kn minus 1 contains a component of S2 minus omega. Take from those points. So Rns will have poles in S2 minus omega and such that I'm taking epsilon to be 1 by 2 power n. So mod Rnz minus Qnz is strictly less than 1 by 2 power n uniformly where for all z in Kn minus 1. This is Runge's theorem applied to Kn minus 1 and I can apply to Kn minus 1 for Qn because of this condition that by construction Qn is holomorphic in an open set containing Kn minus 1. Therefore, I can apply Runge's theorem and I have chosen these as my epsilon and I have got approximating Rns and the poles of Rn are in S2 minus omega. Okay, so we are almost done. This is a crucial step, applying Runge's theorem. And now I'm going to take my f. So I have to construct a meromorphic function, right? I'm going to take my f as, so defined by fz equal to q1z plus n going from 2 to infinity. Take these differences, qnz minus rnz, where these Rn are the approximating rational functions, right? You've got Rn such that this difference is less and you consider all these differences and sum over them. Now let's prove that this f has all the required properties. So choose an n arbitrary and take the compact, in the compact exhaustion take the nth k, kn, and on kn you have f equal to, f is this, right? So this you write as q1 plus 2 to this n, qn minus rn, plus the remaining terms, n plus 1 to infinity, qn minus rn. Okay, you have considered it as sum of 3 terms and each term in the third sum, right? So what we know is modulus of qn minus rn is less than 1 by 2 power n and this is where this is on kn minus 1. So on k capital N you have this is less than 1 by 2 power 1 by 2 power n plus 1. On capital N plus 1 you will have this difference is less than 1 by 2 power n plus 2, etc. 1 by 2 power n plus 2 is also less than 1 by 2 power n. So for each of this n plus 1 onwards, you are getting the modulus is less than 1 by 2 power n. Right, you are getting it to be 1 by 2 power small n only. So for each n small n bigger than or equal to capital N, you are going to get mod qn minus rn is less than 1 by 2 power small n. And this is true at k capital N plus 1, etc. But all of them, right, k capital N plus 1 contains k capital N. So all these inequalities, all these bounds are true on k power n. So each summand, each of the summand, the nth summand is less than 1 by 2 power n. All that is true on k capital N. So each term in the third sum has absolute value less than 1 by 2 power n on k capital N. Okay, and therefore you can conclude that this is uniformly convergent, right? If you get a sequence of a series of functions fn and you want to say that summation fn is uniformly convergent, you can apply the Weierstrass test. What you need is mod fn is less than some constant mn and summation mn should be convergent. So you can take mn to be 1 by 2 power n, summation 1 by 2 power n is convergent and that's happening on kn uniformly. So this is uniformly convergent on kn. So the series converges uniformly on kn. Moreover, the sum is holomorphic in the interior of Kn. Why? Because Qn minus Rn, each of this is holomorphic on Kn, right? Because where are the why is that? Because Qn minus Rn, yeah, Qn is holomorphic on Kn minus 1 and Rn's have poles outside omega. So Qn minus Rn, each Qn minus Rn, each Qn minus Rn is holomorphic on Kn, right? Because Qn is holomorphic on Kn. Each Qn is holomorphic on Kn and Rn is also holomorphic on Kn because the poles of Rn are outside omega. So each Qn minus Rn is holomorphic. So it's a and the series is uniformly convergent. We know that uniform limits of holomorphic functions. We know that the limit of holomorphic functions is holomorphic if the convergence is uniform on compact subsets. This is what we have done earlier. So in particular, the sum is holomorphic in the interior of Kn. So this part is holomorphic in the interior of Kn. Okay, and now if you take f minus this finite part, f minus q1 plus etc plus qn, right? So this part, the third sum is holomorphic in the interior of Kn. This is nothing but f minus this much. So f minus this much is holomorphic in the interior of Kn. That's what we just showed. F minus this much is holomorphic in the interior of Kn. And that is f minus q1 plus etc plus qn and r1 plus etc plus rn. But each of the ri's is holomorphic in the interior of Kn because once again the poles are in outside omega. Therefore, this is holomorphic on Kn. This also is holomorphic in the interior of Kn. Exactly like this in this argument, this here also this is holomorphic in the interior of Kn. But that's what we had to do, right? In order to show that f at alpha has principal part P alpha, we wanted to show that at alpha the principal part is P alpha. Okay, but what is P alpha? P alpha is a summand in Qn, right? So if you take Q1 plus etc plus Qn, in which P alpha is coming once and all other things, the poles are poles are different from alpha, right? In Qn, poles are in alpha precisely for the term P alpha. So if you consider f minus q1 plus etc plus qn, and if you show that this is holomorphic in the interior of Kn, you have shown that by subtracting out the P alpha from here, you are getting removable singularity at alpha, which means the principal part in the Laurent series expansion around alpha, the principal part is precisely P alpha. So you have achieved that. So this is holomorphic in the interior of Kn, but n was arbitrary. So you are showing in this increasing sequence of compact sets, you have shown in the interior it is holomorphic. That means it's holomorphic throughout omega. So this is n varies, but n is arbitrary. So for each n, you are getting a finite sum you can subtract and you are getting holomorphic. So subtracting P alpha, you are getting removable singularity around alpha, which is the meaning of saying P alpha is the principal part. So that's all that we had to show. So F has prescribed principal parts at prescribed poles. So this is Mittag-Leffler. So it's an application. I think there is a proof without using Runge's theorem. Maybe Mittag-Leffler can be done first and then use that to use Runge's theorem. So I'm not sure. I haven't seen that proof. But we are using Runge's theorem for compact sets and Mittag-Leffler follows. Okay, so you can construct meromorphic functions with prescribed poles and with prescribed principal parts at each of those poles. Okay, so any quick question? Is the proof more or less okay? The main idea is What is the main idea? You have taken some, by summing over finite sets, you have taken some nice functions which you are approximating using rational functions using Runge's theorem. This was the main idea. So these differences are holomorphic in omega, and the way you have summed it up, when you subtract that, you are getting removable singularity at alpha, showing that P alpha is the principal part. Okay, read it more slowly later. The argument is conceptually quite simple. Yeah. If there's no further question, let me continue. So this is Mittag-Leffler. Now simple connectedness, we are going to have, so most of this thing we have done, so this is just recalling, so this will be quick. I'm going to have numbers 1, 2, etc. 9 slides. So the next 9 slides will give 9 different characterizations of simple connectedness. Simple connectedness for what? For a region in C. So assume omega is connected, right? Simply connected, the definition is connected and then something happens. So assume it is connected. For a region, we want to give different characterizations. Most of this we have already done, or if not, it's easy. Except one thing, which is the last slide. So the 9th slide will have something which is not easy at all, and except that everything will be easy. Okay, so slide number 9 will have an important remark. All other things, all other 8 slides will have very easy things. Okay, so let omega be a region, and first of all assume, so this is the first characterization, omega is homeomorphic to the open unit disk. Then we want to say it is, so what is the definition of simply connected? It is connected and every closed curve is homotopic to the constant curve. Right, just the constant is a curve, and the trivial curve, the constant curve, and every closed curve is homotopic in omega. Omega homotopic to a closed curve. This is what is the definition of simply connectedness and simple connectedness. And the first characterization is omega is homeomorphic to the open unit disk. So suppose omega is homeomorphic to the open unit disk, we are going to show that every curve in omega is homotopic to a closed curve. So by definition, it's homeomorphic. Therefore, there's a homeomorphism. There's a continuous map from omega onto u. So this is a bijection into and onto such that the inverse is continuous. This is what is given to you. You have to give a homotopy so that a closed curve gamma, any closed curve gamma is homotopy. Given a closed curve gamma, you have to give a homotopy such that it is homotopic to in omega to a closed curve. So for a closed curve gamma, you give me a closed curve and I'm going to give the homotopies HST as, you take gamma of S, this is in omega, you take psi of that, so that's in U, you dilate it with T, T is from 0, 1, so that's in U, right, T is in 0, 1, so when you dilate with T, if something is in the open unit disk and if you multiply by T, because T is from 0, 1, that is again in U, and take psi inverse. These are all continuous maps, right? Psi is continuous, psi inverse is continuous, gamma is continuous. So you do this, so you have got these curves HST. HST are curves. HST are in fact closed curves because H of S at 0 is what? H of S at 0 is psi inverse of 0. And H of S at 1 is these are closed curves because H of, what do we have to show? These are closed curves for every T, these are closed. So H of 0 comma T is what? H of 0 comma T is psi inverse T psi gamma 0, and H of 1 comma T is psi inverse T psi gamma 1, but gamma 0 is gamma 1. So these are also closed because gamma is closed. And what is H? What is at time 0? What happens? H of S at 0. That is psi inverse of 0. So that's a that's a constant curve. It's a constant psi inverse of 0. And H of S at 1 is T equal to 1. So it is psi inverse of psi of gamma s, psi inverse and psi goes, it is gamma s. So h of s at 0 is constant, h of s at 1 is the given curve gamma s. So you have given this continuous homotopies taking gamma s to a constant curve. So it shows that it is simply connected. So this omega is simply connected. Now assume omega is simply connected, meaning every closed curve is homotopic to a constant curve. Then you are going to claim that the index of alpha with respect to gamma is 0 for every closed path gamma in omega and for every alpha in S2 minus omega. Index of alpha with respect to gamma is 0 for every alpha outside omega, meaning for every gamma homologous to 0. For every gamma homologous to 0, but I am also saying this is true for every closed path. So what is the meaning of this statement? Meaning of this statement is that every closed path is homologous to 0. So the claim is if omega is simply connected, then every closed path is homologous to 0. So what is the proof? We have already done this, right? Omega is simply connected. So what is given to us is every closed curve is homotopic to a constant curve. What we have to show is every closed path is homologous to 0. Every closed path is what is our terminology? Homologous to 0. So our terminology, yeah. So we have to show that every closed path is homologous to 0. So why does this follow? We have done this already. So what is given to you is every closed curve is homotopic to a constant curve. So in particular, if you take any closed path, this closed path gamma is homotopic to a constant curve. And a constant path, right? Constant curve, constant path, whatever, it's constant function. And constant paths are homologous to 0, right? Constant paths are homologous to 0 because the index by definition will be, what are you integrating? You are integrating w minus z on the constant path. But when you parameterize a constant path, it's from that point to itself. Therefore, all the integrals are 0. So index is 0 on the constant path trivially. Index is 0. So constant path is homologous to 0. So if you give a closed path gamma, it is homotopic to 0, but homotopy implies homology. Therefore, it is homologous to the constant path, but constant path is homologous to 0. Therefore, this is homologous to 0. Okay, so this is something that we have already done. Now, third condition, suppose this is what is given to you, that every closed path in omega. So in each slide, the hypothesis is what is proved in the previous slide. We are showing, A implies B implies C implies D implies etc. So assume every closed path in omega is homologous to 0. Then we are going to claim that S2 minus omega is connected. So S2 minus omega being connected is another characterization for simple connectedness, because we are assuming omega is also connected. Okay, for a region omega, S2 minus omega is connected is another characterization. We are going to deduce that from the fact that every closed path is homologous to 0. So suppose not. Suppose S2, so assume that every closed path is homologous to 0 and assume that S2 minus omega is not connected. If S2 minus omega is not connected, you can write it as a disjoint union. I am putting this dot here for disjoint. Disjoint union of two closed sets. H and K are closed sets, and the disjoint union gives you S2 minus omega because you are assuming S2 minus omega is not connected. So in S2 minus omega has infinity, so infinity will be part of one of this. Assume that H contains infinity. H is the component containing infinity. Assume. Now you take a W to be the complement in the plane of H. Okay, so H is the unbounded part, and you take the complement of H in C. In other words, you are writing W as, so W is such that W is omega union K, right? K is the other part, closed set, and K is the other part, the part other than H of S2 minus omega. So the meaning of this is you are taking omega union K as W, right? W is omega union K. Now consider for K, so K is contained in W, and for K contained in W, apply compact CIF. What is compact CIF? If you have a compact set, right? K is a compact set, no? K is a closed set and it is bounded. So it's closed and bounded, so it's compact. So if you have a compact set contained in an open set, compact CIF says that you can take a cycle in W minus K such that the Cauchy integral formula is true. Fz is 1 by 2 pi I integral Fw dw by W minus Z. Okay, so apply compact CIF to the function f is 1. F is identically 1. F is identically 1. Okay, so what will you get? You will get a cycle gamma where in W minus K. Compact CIF, the point was that you can choose a cycle in W minus K. So we get a cycle in W minus K, which is omega. W minus K is omega. You get a cycle in omega such that index of Z is 1 for Z in K. Right? What you will get is actually you are not using the final thing of compact CIF, you are only using the proof of compact CIF. Proof of compact CIF constructs a cycle such that index of Z with respect to gamma is 1 in K and this index is 0 outside omega. That's what it does. Index of Z with respect to gamma is 1 on K and it is 0 for Z outside omega. So it's a proof of compact CIF, or you can apply the final formula for F equal to 1. So you would have got such a curve, and therefore this claim is not true, that every closed path in omega cannot be homologous to 0. Right? Every closed path in omega is homologous to 0 is not correct, because you have got a cycle which is not homologous to 0. A cycle comprises of closed paths. So if every closed path is homologous to 0, then every cycle is homologous to 0, but that's not true. You have got a cycle which is not homologous to 0 in omega. So that proves the claim that S2 minus omega is connected. Otherwise, you have got a contradiction. Okay, so this is the next characterization, that S2 minus omega is connected. Now assume S2 minus omega is connected, and then we are going to claim that every holomorphic function in omega can be uniformly approximated on compact subsets by polynomials. But this is something that we have already done, right? How did we do this? This was corollary to Runge's theorem. If S2 minus omega is connected, that prescribed set of poles A you take as singleton infinity, and then every holomorphic function in omega can be uniformly approximated by rational functions whose poles are only in A. So you can approximate by rational functions whose pole is only infinity, but pole infinity, rational function pole infinity meaning polynomials, and the approximation is uniform on compact sets. So this is just a corollary to Runge's theorem. If S2 minus omega is connected, by taking A equal to infinity, you have shown that every f can be uniformly approximated on compact subsets by polynomials. Now assume every holomorphic function can be uniformly approximated on compact subsets by polynomials, and the claim is something like Cauchy's theorem. Integral gamma fz dz is 0 for every f in h omega and for every closed path gamma. Okay, so what you are assuming now is that any holomorphic function can be uniformly, omega is such that every holomorphic function can be uniformly approximated on compact subsets by polynomials, and we are going to claim that integral fz dz is 0 for every closed path gamma and for every holomorphic function f. That's easy because you what is given us you can approximate by polynomials on compact sets. Take gamma star. You give me a closed path gamma, take gamma star, that's a compact set. Given any holomorphic function f, it can be uniformly approximated by polynomials on gamma star. So take Pn converging to f uniformly on gamma star, and then because it's uniform convergence, integral f is integral limit Pn. Limit can be taken outside because of uniform convergence, so it is limit integral Pn. But integral Pn z is 0 is obvious, right? Because integral z power n dz is 0, because z power n has a primitive z power n plus 1 by n plus 1. So integral of polynomials is obviously 0. So limit of that is 0. So this follows. Okay, so from this condition that it can be approximated uniformly by polynomials, integral is 0 for every closed path and for every holomorphic function that follows. Now in the sixth slide, you assume that every holomorphic function can be uniformly approximated by compact sets. No. In the next slide, you assume that every holomorphic function and for every closed path, the integral is 0. And you're going to claim that every holomorphic function has a holomorphic primitive. So assume this, that the integral is 0 for every f and for every closed path. Then the claim is that every holomorphic function f has a primitive g such that g prime is f. Every holomorphic f has a holomorphic primitive. What is a proof? Proof is something that you have seen long back in calculus, and also in we have done it in this course also. So standard argument, fix a point z0 and take any path connecting z0 to z. Why do you have a path connecting z0 to z? Why do you have a path connecting z0 to z in omega? Because omega is connected. Omega is a region, therefore it's connected. Therefore there is some path. Choose any path. Okay, and you have to, in order to show that antiderivative exists, you have to give a candidate and then show that the candidate, the function is well defined, and then show that its derivative is actually that standard argument. So define the candidate primitive capital F by integral over this path f zeta d zeta. Note that this is well defined. Why is this well defined? This is well defined because of this condition. Because if you have z0 to z one path and z0 to z another path, joining these two paths, you have got a closed path, right? Go this way and come in the opposite direction via the other path, and on that the integral is 0, meaning that this is well defined. So well definedness is exactly this condition. And how do you check that f prime z is f zeta? From first principles, take fz minus fz naught by z minus z naught limit as z going to z naught. Apply, you can take the limit inside, etc. Standard argument from first principles, check that this is a primitive. So this is the next condition. Now in the next slide, you assume that every holomorphic function admits a holomorphic primitive, and you are going to claim that every non-vanishing holomorphic function has a holomorphic logarithm. If you have a function holomorphic which is never 0, then log f makes sense, and log f is holomorphic. So this is what we have to show. Okay. So this also, this underlined statement, this is the important part. This tells you what the proof should be, and we have seen this proof. If f is given to you and f is non-vanishing throughout, then of course 1 by f makes sense. So you argue with f prime by f. F prime by f is holomorphic. And you know that every holomorphic function has a primitive. So f prime by f has a primitive, let us say g. So g is holomorphic and g prime is f prime by f. And we have seen this argument before. You can take derivative of f times e power minus g, and you can show that this is identically 0. Why? Because g prime is f prime by f. So if you take the derivative of this, you will see, so from g prime is f prime by f, by cross multiplying, you will see that the derivative of this is identically 0. And because omega is connected, this is a constant. By adjusting for the constant, f is exponential of g, right? This is a constant. You can adjust the constant so that f is of the form exponential of g. This is the meaning of saying that f has a holomorphic logarithm, because f is exponential of g, then we say that log f is g, and g is holomorphic. That's the point. G is holomorphic throughout omega, so log f is holomorphic throughout omega. So every non-vanishing holomorphic function has a holomorphic logarithm. So this we have seen in the argument, right, in OMT, when we wanted to prove OMT. We showed that there was an argument using taking mth root, and taking mth root, this was the important step. So this we have already seen. And in the next slide, we are going to assume that every holomorphic function has a holomorphic logarithm. Every holomorphic function has a holomorphic logarithm, and then we are going to claim that in that case every holomorphic non-vanishing holomorphic every non-vanishing holomorphic function has a holomorphic logarithm, and we are going to claim that every non-vanishing holomorphic function has a holomorphic square root. But we have seen this already, right? I mean, if f can be written as e power g with g holomorphic, you just take phi to be e power g by 2. We have in fact taken nth root earlier in the proof of OMT. So take g by 2 and define phi to be thus. Phi is holomorphic because g is holomorphic, therefore g by 2 is holomorphic. E power g by 2 is holomorphic, so phi is holomorphic and f is phi square. So in other words, phi is the square root of f and phi is holomorphic. So if every non-vanishing holomorphic function has a holomorphic logarithm, then every non-vanishing holomorphic function has a holomorphic square root. So what remains? So we have 9 characterizations. So what remains? The remaining claim is that if every non-vanishing holomorphic function has a holomorphic square root on omega, we have to show that omega is homeomorphic to the open unit disk, right? We have been showing 1 implies 2, 2 implies 3, etc. 3 implies this. I mean, finally we got this. We have to show that 9 implies 1. This is the 9th statement, that every holomorphic function has a holomorphic square root, and we have to show that omega is homeomorphic to the open unit disk. So there are 2 cases. Suppose omega is the whole complex plane, right? Omega is a region in C. Suppose it's a whole of C. Then there's nothing to show. Whether some condition is given to you or not, it's anyway homeomorphic to you. Which this is just point set topology, that C is homeomorphic to the open unit disk. So the point is, what if omega is not C? If omega is properly contained in C and it is simply connected. But simply connected can be, some very complicated way it can be simply connected. Still, it is homeomorphic to the open unit disk. What is given to you is that every holomorphic function you can extract a holomorphic square root. So otherwise this is not easy at all, not obvious at all, but we are going to show something much more. We are going to show that if omega has the property, if omega is a proper subset of C, it's not the whole of C, and it has the property that every holomorphic function you can extract a holomorphic square root. We are going to show that not just it's homeomorphic to U, we are going to show that it is biholomorphic to U. There's a holomorphic map which is also a bijection from omega to U, such that the inverse map is also holomorphic. I quickly mentioned this in the very first lecture. Does anyone remember the name of this theorem? It's a very, very famous theorem. I had verbally mentioned this once. A proper subset of C, if it is simply connected, then it is biholomorphic to the open unit disk. But the way we are going to do later is that instead of simply connectedness, the property that we are going to use is it has a holomorphic square root. That's the property that we will use. Every holomorphic function has a holomorphic square root. Using that, we are going to show that there is a holomorphic function from omega to U bijection, and inverse is also holomorphic. Does anyone want to make a guess what this theorem is? We had stated a number of name theorems. This is one of those.
Was it Riemann mapping theorem?
Yeah, very good. Yeah, it is Riemann mapping theorem. Mamta, right? Yeah, it is Riemann mapping theorem. So this is the celebrated Riemann mapping theorem. So this we are going to do later. So assume this is also there, then we have proved everything. So except Riemann mapping theorem, which is going to be used in the very last implication, everything else is obvious. I mean, not obvious. I mean, we have proved, either proved earlier or proved now. So these are the characterizations of simply connected domains. So we have some more time. So I thought I will take this up in the discussion, but maybe I'll do this projecting also as part of the class, and then we will stop. So let us project from one page from Conway and one page from Rudin. Conway is not. Conway is more general. I just wanted to read a paragraph from Conway. some generality about this thing. He calls this previous result that we have proved characterizing characterizing a region, characterizing simple connectedness for a region using all these different characterizations. He calls this an aesthetic peak. It's the highest point that you can reach. I mean, in terms of beauty. Okay, appreciating how beautiful something is, aesthetic peak. So let's just read that paragraph in Conway. So that's page 204. We will project that. And then just for fun, I want to, point out something from page 274 of Rudin. Okay, so 204, 274. So let's project that. So I should first take, first we will do Conway. Conway is at page 204, so maybe some more pages, 214. Yeah, 204. So he proves this result. All these things are equivalent. And then he says, you can see this, no? Then he says, this completes the proof of the theorem. Proof is over. This theorem constitutes an aesthetic peak in mathematics. Aesthetic meaning, something about beauty, etc. Okay. Aesthetic peak in mathematics. Notice that it says that a topological condition, simple connectedness, is equivalent to various analytical conditions. Existence of, okay, we can also show, existence of harmonic conjugates, which I haven't done, but that's also part of this. And Cauchy's theorem, right? Integral f is 0 for each f. So those are analytical conditions, as well as algebraic conditions, existence of a square root, right? Existence of a square root is an algebraic condition, you can say. Of course, it's also analysis because we are saying holomorphic square root. Anyway, it's connecting topology with analysis and algebra and other topological conditions. So that's why he's calling it an aesthetic peak. This certainly was not expected when simple connectedness was first defined. Nevertheless, the value of the theorem is somewhat limited to the fact that simple connectedness implies these 9 properties. Although it is satisfying to have the converse of these implications, it's only the fact that the connectedness of C infinity minus G implies C infinity is his notation for S2. S2 minus omega, G is his notation for omega. So it's only the fact that the connectedness of S2 minus omega implies that G is simply connected, which finds wide application. So this is, some things from experience. Only that property is really used, and we have also used it, right, in corollary to Runge's theorem. So no one ever verifies one of the other properties in order to prove that G is simply connected. And to see that, how complicated looking it can be, a simply connected region, you take an infinite spiral. You take from the origin and you take a spiral going to infinity, right? A spiral curve, and you take the complement of that. Then S2 minus so omega is the complement of the infinite spiral. So S2 minus omega is the spiral together with the point at infinity. So that is connected. Therefore, such a thing is simply connected. So simply connected things can be, can be somewhat complicated. But the point of Riemann mapping theorem is even such things are biholomorphic to open unit. Just think about it, right? You remove this infinite spiral from the complex plane, and the remaining part is simply connected. So there is a holomorphic map, a biholomorphic map between the complement of the spiral and the open unit disk. That's Riemann mapping theorem. So it's quite powerful, very nice. Okay, this is the first part I wanted to project. Second thing that I wanted to project is Rudin page 214. But this is, no maths here. It's just for fun. Yeah. 214. So let's go to 224, approximately 214. Yeah. Oh, no. This is not where I want to be. So maybe I made a typo here. No, 274, right. if I go to 284, so 274, this is the characterization. So I hope all of you can see. So how many slides we had? We had 9 slides, right? So this is exactly what I proved, and I have given you Rudin's proof. So we have proved A implies B, B implies C, C implies D, exactly in that order, and last thing is this implies this. There exists phi in H omega such that F is phi square, so holomorphic square root, right? All of you agree? And here is my fun question. So how many conditions are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Just count nine things, and just count on the left, A to J. Now tell me how many A to J, how many alphabets are there A to J? Can someone quickly tell me? Just count A, B, C.
10.
10.
There should be 10.
There should be 10. Who's this? Is this Aryaman? I mean, I have
Yeah.
yeah. There should be 10. So
I is missing from his
okay, you told that I was going to say you don't say it, and I was going to ask this. Okay, fine, good. Okay, so this you had noticed it long back or just now, Aryaman?
When you put it, I keep in mind what the multiples of 5 are. So I know that J is 10. So I
Say
thought
that
that he
again.
had one more condition.
Say that again. You already knew.
In my mind, I know that J is the 10th letter.
Oh, this you already knew. Anyway,
Yeah,
always
so
after E anything I have to count from starting. Only then I know which
so I
sufficient.
have a thing for remembering the multiples of 5. So it's easy to locate the others.
Okay, so E you know, J you know. Okay, tell me what is 15 then.
So it's HOT. So it's EJOTY.
Okay. Okay, fine. Yeah, good. So I is missing. So this much I knew, and I always, used to make this fun observation that something is missing, and I might say something like, why am I missing or something like that. Okay. But then I was talking to one of my colleagues, and then he gave me an explanation why I is missing. So it is very much plausible. Of course, one cannot prove it. You want to take a guess, Aryaman, why I is missing?
Because I is used for the complex unit.
Yeah, so this what he told me, and old style this thing. So let's just see where he uses I. The way one prints I, it is not our I. See in my slides, I has a different notation, right? Whenever I don't know whether I have used I in this slide, but my I is LaTeX I math, which comes with a particular I without a dot. But old books like Rudin's I is the usual I. So I cannot quickly see an I anywhere. But his I is a usual I. So if he had put an I here also, doesn't matter. Anyone would have understood from context. But I think that's the reason why one avoided. Yeah. So your explanation is exactly my colleague's explanation. Okay. So that's for fun. Okay, so let's stop the recording here and go to the discussion session and discuss several things. So I must also say that there is something which we haven't fully proved from last class, and if you look at Moodle, I have struck it out, one of my assertions, and I haven't replaced. In fact, I did replace, but then I had a WhatsApp conversation with Aryaman, and he pointed out a flaw, a possible flaw, and I removed it from Moodle. I will do it as soon as I have a nice proof. I will put it back on Moodle, and we can discuss that also. So let's go to the discussion session. So let me stop sharing. And let me also stop recording.